Electronic devices have rapidly become part of our day-to-day lives. We wake up and check our phones. We use our phones or our cars to tell us how to get places. Some of us even yell at our Xbox Connects to turn on. We have access to everything at our fingertips. So, as you can imagine, in the world of digital forensics, everyone's going to have a phone or a laptop or something that will link them to the rest of the world that we can use to gather information. So as a computer science major and a student, or as a computer science major, my concentration is cyber forensics and security. I would like to inform you all of the basics of digital forensics and how hashing functions work to verify data. So let's start by explaining digital forensics and hashing. So digital forensics is, according to Garfinkel, the uncovering and examination of evidence located on all things electronic with digital storage, including computers, cell phones, and networks. So everyone uses electronic devices, and investigators will collect these to gather information and evidence on suspects or victims. So hashing is defined by Garfinkel, again, as probably the single most transformative technical innovation in the field. First, as a means for ensuring integrity of forensic data, and later as a way to recognize specific files. They're mainly, as I just said, intended to, in the world of computer forensics, they're mainly intended to make sure that the original copy of data is the same one that was worked on by the technician when they're proving that someone had this or that on the computer. So hash functions take an input of an arbitrary length, so it could be a 200-page text file, a 3-word little notepad note, or an entire terabyte hard drive. And it will convert it to a fixed size output, which is going to be about 128 bits long. In most cases, this could be 256 or 512, but just for verification, you'll usually only get 128 bits. Hash functions are said to spit out a unique output for everything that's put in. So basically, it's like a fingerprint. Everyone has their own, like theoretically, someone might have very similar ones, but when you look at it as a whole, you will almost never run into two of the same hash outputs. So some examples of how they're used: to protect credit card numbers when you send those over the internet. Certify the integrity of code run on iPhones. So any app you downloaded, it'll take a hash value and compare that to what's on their server. And then that is how it's going to know that you downloaded the correct file. And it's also used to validate keys to play music. So this has a lot of day-to-day applications that you may not know about, but it's used from everything to just storing a password on a website to criminal cases in court. So now that I would like to run a quick demo for you guys, just so you have a better understanding of how it works. Sorry about that. So right now, I'm going to take two files and show you their hash outputs. So we have this demo.docx, which is basically my speech outline, as you can see. At the moment, demo 2 is going to be the exact same file. The only difference is the name. Once again, it's my speech outline. So we can take this and we can pull an MD5 and a SHA-1 hash. These really long and confusing numbers that you guys see, those are those hash values. That is what's spat out from that arbitrary length input. Now the other file, it's the exact same as you can see. This number right here is going to be the same as this one, and it's the same for the SHA-1 hash. Now if we go to this demo 2, and we change anything, could be change the font or the facing. In this case, we're just going to make this a lowercase h. We're going to save it. Now I'm going to pull up the first and most hash values. You can see at the bottom. This is the first and most hash value, and this is the new value for the second one. So just by changing the case of that character, it completely changed the 2 hash values. So just by looking at that, you can tell that even a minor change of a file or a hard drive, even if it's just 1 bit, that will completely change the hash value of that hard drive. So now that you have a basic understanding of how that works, we're going to talk about how the 2 combine. So how hashing and computer forensics actually work together. So when a computer forensics investigator goes to collect their evidence, they're going to use a write blocker to ensure that nothing's changed when they're copying the evidence from the scene, the victim, suspect's device. Now, the hard drive image, that is a copy of the data they're working with. So they make sure that that never changes, and they do this by getting one of those hash values. And then they make a copy of that, and that copy, they verify that it's exactly the same by that hash value. So you can see in this image that the original hard drive has this hash value, and the clone hard drive has the exact same hash value. So this is how you can prove in court that what you're working on is exactly the same as the original piece of evidence. So, as I was explaining earlier, when you hash an image, you get those unique values. If the hash values of 2 images are the same, they will 99.999 repeating percent of the time be the same. Like a fingerprint, you have that very, very, very rare chance that it could be different, but that will almost never happen. The only example of this is a forced hash collision in the MD5 and SHA-1 algorithms, where you can change a few bits and you can still receive the same output. But there's studies shown that even if you have 2 files with the same hash value, if you put those in the exact same location on that hard drive's framework, that it will still change the overall hash value of the hard drive. So at the moment, hash collisions are not a significant problem, and hashing is the best way that we can show that the piece of evidence that we worked on is the same as the original evidence without altering the original evidence. Because the ultimate goal is to make sure we have that original copy so we can prove that this was on their hard drive or this or that. So you should now have an understanding of the importance of hashing in a computer forensics standpoint. So today I summarized the basics of hashing. If you get nothing else from this, I hope that if you're on a jury with a crime that has digital evidence, that you remember just how powerful hashing is, and that if they present you 2 hash values, if those are the same, the 2 drives they worked on were the exact same. So you can trust that when they're working on that, they could not have planted evidence, or it couldn't be a error. Those 2 hard drives are the exact same, and whatever they present to you is going to be true. Thank you.
Say.
How did you get into this?
How did I get into this? Honestly, I've just been a big fan of computers since I was young, and it looked like a very interesting thing.